Well, let's go and review some things that we talked about yesterday as we began talking about this word a lot yesterday, and that's the ability to do work or change matter. And obviously in this class we're looking a lot at the changing of matter, but what do we call the ability to do work or change matter? Olivia? Energy. It's what this class doesn't have right now. Grace, if you could see them. They're all like practically passed out, so we're going to see how we get through the hour. But energy, the ability to do work like chemistry or change matter. Now we talked about two major types of energy. One is energy of motion. Okay, you're not in motion, but if you were, Nick, you would have kinetic energy. And when you're sleeping, you're not in motion, but you're resting up, so you could be in motion later. Don't sleep right now, though, Abigail. What do we call the energy an object acquires when it's exposed to a force? Potential energy. And of course we said there's both chemical potential energy and of course what we're more accustomed to is actual movement. But on the chemical level, right, atoms, molecules moving around, there's kinetic energy there. We said that in some cases there's the potential for energy to be released. Chemical potential energy, like in dynamite, chemical potential energy. It's just sitting there. All it takes is a little impetus, a little flame down the fuse, and then, of course, we have plenty of kinetic energy, just chemical kinetic energy. What do we call the study of energy changes that occur in chemical reactions? The study of chemical changes that occur in chemical reactions. Olivia? Chemical thermodynamics, good. And as we study these chemical changes, we said that the sample itself that's being studied can be referred to, Nick, as the system, right? The thing that we're studying itself is the system, and literally everything else around it would be called everything that surrounds the system could be referred to as its class surroundings, right? Everything else is a surrounding. So for instance, if we were looking at the energy in a test tube, okay? And we've got a test tube with acetic acid, we dropped a little piece of magnesium in it and crazy bubbles forming and stuff like that. Okay, the test tube itself, the chemicals inside, all of that would be called the system. And then you holding it, or the test tube holder, the lab table, everything in the air around it, that's all the surroundings. And we said that if the system doesn't allow other matter to get into it, for instance, if we put a stopper in the test tube so that other air can't even get into the test tube, then we would have what kind of system? Back to Abigail? A closed system. However, we understand that there's the potential as we're holding the test tube to feel, well, it's getting warmer and energy is being released from the test tube. But if we insulated it really well, so that not only cannot matter get in, but no energy escapes either, now we've got not just a closed system, but an isolated system. Good. We said that the energy inside the system is referred to as its what? Nick? Internal energy. And we said, can we measure the internal energy of a system, class? No. You can't measure the internal energy of a system. What you can measure, however, Olivia, you can't measure the energy the system has, but you can measure any, represented by delta, anybody? Changes, there it is, Nick, changes of energy. Energy is what we call a state function, and so it can't actually be measured, but you can measure any changes that take place in the energy. What letter do we use to represent internal energy? Olivia, back to you. Well, capital E is energy, and so since we can't actually measure energy or internal energy, we'll be measuring delta E, changes in energy. We said that changes in internal energy are caused by or affected by two things. What are the two things that affect the internal energy of a system? Abigail? Two things affect the internal energy of a system. You can cause it to have more energy if you add something to it. I can't quite hear. Heat. If you add heat to it, good. So the changes in energy are affected by heat, and then also it's affected by if you do something to it or if you allow it to do something, and that would be, Nick? Work. There we go. Heat and work. Now, in equation form, we use a letter for heat, and it doesn't make a lot of sense. Like, I get internal energy, E energy makes sense. Heat, the letter makes absolutely no sense, class. Capital Q. That's heat. Lovely. All right, and then work, well, that was a little bit more logical, class. That's simply... So remember we said that if the work is being done by the system, it's expending work. Would that raise or lower the internal energy, class? If the system does work, it would lower the internal energy. For instance, let's just suppose, and I don't think this would happen, but let's suppose we stoppered our fizzing substance in the test tube, and suppose the pressure built, and suddenly, pop, the whole stopper just pops right off. Well, that means the system just did work to displace the stopper, correct? If it did work, it just lost energy because it transferred its energy into the stopper to make it go flying off, which would be bad because there would be other stuff coming out with it. Sad day, right? Or if it's releasing heat, right? If it releases heat, it begins to feel warmer. It's giving off that energy if it's not an isolated system. So gaining heat would cause an increase in internal energy. Having work done on it would cause it to increase energy. More often than not, it does work and expends energy, or perhaps gives off heat and expends energy. So the energy changes can be either positive or negative. But we did say this, that for gases, internal energy is really not a sufficient describer of what's going on, because along with heat, right, we think of heat, we think of temperature, there are two factors that affect the temperature of a gas. What two factors will always affect the temperature of a gas? Thinking back to Charles's law, the combined gas law, what other factors affect temperature? Anyone? Pressure and volume. Good, Nick. Class, what affects temperature? Pressure and volume. So we have to account not just for the energy, but if we're talking about a gas, we need to account for the pressure and volume of the gas as well. What term describes the internal energy of the system plus the product of volume and pressure? What term is the energy of a system, internal energy of a system, plus the product of pressure and volume? Enthalpy. Enthalpy, and that's a term we're going to talk about a lot today. Enthalpy is the internal energy plus the pressure and volume. And what letter do we use for enthalpy? Do you remember, Abigail? H. Now in the service lane, oh great, H. That also makes no sense. But if we remember, and we're going to talk about this a little bit more today, that enthalpy almost always ends up equating to heat. H for heat, H for enthalpy. It kind of makes a little bit of sense. Again, enthalpy also cannot be directly measured, but changes in enthalpy can. That's one of the things we're going to be looking at today is how does enthalpy change in the course of a reaction? What unit do we use for work and heat and energy and enthalpy? They all have the same unit. What unit would be used for all these different forms of, in a sense, energy? What's that unit, Nick? Good, the joule or the kilojoule. So joule, named after James Prescott Joule, not joule as in like ring on finger with joule in it, represented by J. Or oftentimes, remember we said that a joule is such a tiny unit that we'll usually measure them by the thousands, kind of like pascals. So tiny we usually measure in kilopascals. We'll usually default to the kilojoule, but those are the units we would use for any of these, not pressure and volume obviously, but all the other letters up here would be represented in terms of joules. We talked about two types of reactions yesterday. We're going to look at them more today. Reactions that, when they occur, either absorb energy into the system, usually absorbing heat, or they would release energy from the system. What are the two types of reactions we looked at yesterday? Abigail? Good. Endothermic and exothermic. So here's the question. Which of those, endothermic or exothermic, causes energy to be released by the reactants? They react, and when they form the products, energy is also released. That would be an exothermic reaction. So again, I don't know that you necessarily need to think through the whole formula here, but you have your reactants, and of course they produce the products, but if they also produce heat with the products, that's exothermic. Energy is being released out of the reactant. Would an exothermic reaction typically feel warm or cool? Abigail? If it's releasing heat, would it feel warm or cool? It would feel warm because there's heat being given off. The endothermic reaction then, class typically would feel cool because it's absorbing energy in order for the reactants to react. And by the way, oftentimes in an exothermic reaction, there may be some heat involved in the reactants as well. It just produces more heat than it uses in the first place. but the reactants have to have heat in an endothermic reaction to produce the products. Well, in that case, the heat is being absorbed into the reaction, into the reactants, in order to make the products occur. It's absorbing heat, it's sucking that energy in, hence endothermic, usually feeling cool to the touch. So for an exothermic reaction, since heat is being given off, we could say that enthalpy is being gained or lost, class? It's being given off. Right, think about giving away money. If you give away money, is that a loss or a gain for you? Well, you might gain friends, possibly. I don't think they'd be the right kind of friends, but you might gain friends, or people who suddenly call themselves your friends. If they're a junior high, don't trust them. But if you're giving away money, that's a loss for you, correct? Well, if it's giving off heat, that's a net loss. So we would expect to see a negative change of enthalpy. We'll be seeing that today. That sounded bigger than a volleyball somehow. Anyway, maybe somebody's walking up there. I don't know. That sounds like somebody's walking. Like maybe somebody went up there to get a ball. I don't know. Anyway, that's totally random. And then endothermic reactions. Since the energy is being absorbed in, that would be like all of you giving me money. That would mean money's coming in. I'm gaining money, increasing total enthalpy in the system. Does that make sense? This is all stuff we talked about yesterday. Now, let's build on that a little bit here. Going back to something we'll keep going back to a lot is your chemical equations. Remember, the first thing we talked about with chemical equations was balancing the chemical equations? And we said when we balance them, we just make sure the coefficients and the numbers all work out, that the total number of hydrogens between coefficients and subscripts, they all match up, right? And so we learned how to balance chemical equations. And then we said, well, there's different types of chemical equations, like their combination, decomposition, single displacement, double displacement. Remember all of that? And then we said, well, based on molar mass, we could say if we have this many grams of this and this many grams of that, one of these will be the limiting reactant. And based on that, we can expect to get this many grams of this other substance. Do you remember doing that? We could predict how much of something we would get in a reaction. We can do that with enthalpy as well, or energy, or heat is another way to think of a very similar idea as we track a chemical reaction. We can say, okay, based on these reactants reacting to produce this, this is how much energy or enthalpy would be given off or absorbed by the reaction. We could predict whether it would be exothermic or endothermic. So that's what we're going to be looking at today, is this enthalpy of reaction. Here's the next term to write in your notes. Enthalpy of reaction. Enthalpy of reaction is the total energy released or absorbed once the reactant, or once the products rather, are the same temperature as the reactant. So enthalpy of reaction is the total energy either released or absorbed once the products are the same temperature as the reactants. Now, obviously, if it's endothermic, initially the reactant, the products are going to be colder, right? If it's exothermic, then initially the products are going to be warmer. Once the temperatures have leveled out, did we end up gaining or losing energy in all of this? That's what enthalpy of reaction is. Does that make sense? Total energy absorbed or released once the products are at the same temperature as the reactants. I mentioned it yesterday, I don't think I had you write this down, but put a star next to this if you would. If pressure is constant, and again, for our purposes, it generally will be, right? The room doesn't suddenly, man, there's a lot more pressure in this room before I started doing this experiment. No, the pressure's not going to spontaneously change. So typically the pressure will be constant. Assuming pressure constant, the enthalpy of reaction, the change in enthalpy once the reaction occurs, will equal the heat that is either absorbed or released. We could say the heat that's exchanged. Might be a good way to put it, exchanged with the surroundings. So assuming pressure is constant, which we will, then the enthalpy change is simply going to equal whatever heat was exchanged with the surroundings. So again, that's another reason why enthalpy is represented H, because a lot of times, practically speaking, we're talking about heat. Now we need to understand there's a whole lot of different substances we've looked at. Their chemical symbols and stuff like that. We've learned how to name them if they're molecular compounds. If they're ionic compounds, we learned how to name those. And we kind of talked about these different things. Well, all these different compounds that exist out there, as they are forming, are either formed exothermically or endothermically. For instance, water. When it's produced, hydrogen and oxygen, it takes heat to get hydrogen and oxygen to release, right? Hydrogen naturally has bonds. Oxygen naturally has bonds, right? H2O2, correct? If you can break down the bonds of the hydrogen with each other to allow them to accept an oxygen and allow the oxygens to separate so you have a free oxygen to bind with other hydrogens, heat will be required, but then as they produce water, they also produce a great deal more heat. It's an exothermic reaction. It takes heat to make this compound that we call water. Hydrogen, oxygen, to make water. And so if you look in your textbooks there, page 111, it actually kind of shows you how this works. 6.68, a little green box there on page 111, shows you have two hydrogen, well, 2 moles technically, right? That's what the coefficients mean. 2 moles of hydrogen plus a mole of oxygen. It can produce 2 moles of liquid water, plus it gives off heat. It gives off, or loses, we could say, 571.6 kilojoules of heat. That means that to form H2O, it's going to use up 576.1. Did I type that number? Write that up? Yeah. 571.6 on those decks. 571.6 kilojoules. But it gives off that. If it's giving it away, class, that is... You give away, that's a loss, right? So we're going to say that it's negative. This is our change in enthalpy just to make water. Does that make sense? To make water, it takes that. Now that's to form, notice, 2 moles of water. Well, that means to make 1 mole of water, which again, whenever we're doing our equations, we don't do what they show down here, right? Equation 6.7, we don't use fractions. We don't do that, okay? But if we're trying to get 1 as the coefficient of H2O for 1 mole, well, we just divide by 2, right? Cut that number in half. 2 moles takes that much to form. So then a single mole would require half of that, which is, I'm not going to be lazy and say 285.8 kilojoules. To make a mole of water takes a loss of 285.8 kilojoules of energy, of heat. Does that make sense? Not all reactions, formations require a loss of heat. There are endothermic reactions as well. For instance, turn the page. And you look at, well, what about forming like nitrogen dioxide? Well, when nitrogen dioxide is formed, it actually has to absorb more heat than it will produce. It absorbs heat, produces nitrogen dioxide. The nitrogen dioxide's at a lower energy than the products had to be, which means it absorbed heat, meaning it's a positive change. So to produce, it says 1 mole of nitrogen dioxide. I think it's like 33.2 kilojoules. Okay, so to form 1 mole of nitrogen dioxide, 33.2 kilojoules. Well, notice that's positive. That's because it's an endothermic reaction when those elements come together to form these things. Now, where does that come from? Well, we have to assume the elements themselves are at 0 joules of energy inherently. And frankly, a molecule on its own just in existence, or an atom on its own just in existence, doesn't have a whole lot of heat or energy. The heat comes when they try to combine. Either they absorb the heat or release the heat. So this gives us something that we call an element's standard state. An element's standard state. The change in enthalpies that we're forming this water or forming nitrogen dioxide assumes that there wasn't an energy level to begin with. We want to assume 0. So for this, we would reference the standard state of an element. Standard state needs to have something defined though. First of all, the pressure needs to be sort of established. This is what we're expecting the pressure to be. For our purposes, we'll say 100 kilopascals. In STP, that's the standard pressure. That's kind of what we'll assume. Well, what about temperature, right? STP assumes 0 degrees Celsius. Is 0 degrees Celsius the most common temperature in a laboratory? No, that's one cold laboratory. Okay, no, that's not standard. So for our purposes, the standard state, we're going to define 25 degrees Celsius as our room temperature. That's where we're going to assume at that point, all elements have an energy level of 0. So if you just have nitrogen, we're assuming 0 energy from that. You have oxygen, 0 energy. When they combine, they have to absorb this much energy then to form nitrogen dioxide, but we're assuming they're starting at 0. So for hydrogen and oxygen to form water, well, we're assuming the hydrogen has 0 joules of enthalpy, the oxygen 0 joules of enthalpy, but they give off, when they react, this much net, negative 285.8 kilojoules of enthalpy as it forms, so that many joules of heat as it forms. We're assuming we're at standard state. Again, standard state has to be defined with a set pressure and, more importantly, a set temperature. Now, granted, 25 degrees Celsius, normally we would think, 298.15 Kelvin, but that's where we're at for that. So, what about if water were to react with nitrogen dioxide, for instance? Well, the very formation of water required a loss of energy, right? Negative enthalpy change. The very formation of nitrogen dioxide required a certain enthalpy change. So what if compounds react with each other? We can predict whether their reactions will be endothermic or exothermic by tracking what we call the enthalpy of formation. The name is literally what it suggests. Enthalpy of formation literally is tracking how much enthalpy was gained or lost in the formation of this compound. Again, elements, we're going to assume we're at standard state, so they have no enthalpy whatsoever. It's 0 joules. But for all the compounds, we have to assume, well, there's some enthalpy that was used in the formation of this compound. That's what these two numbers are. 1 mole of water, negative 285.8 kilojoules of enthalpy just to form it. Okay? Nitrogen dioxide, 33.2 kilojoules of enthalpy just to form it. And if you look at page 112, there's a whole table here of all these different enthalpies of formation, again, assuming 25 degrees Celsius, standard state. Well, if we look at all these, notice a bunch of them are negative, and some of them are positive. Remember, what does a negative enthalpy change mean? Loses, which means it's giving off, which means it's exothermic. Anytime you see a positive, that means it's drawing in, which makes it endothermic. So there's a whole slew. Some of these are exothermic, some of these are endothermic in the way that they are formed, so that when they react, what's going to happen from that? So let's look at a few of these. The first example your book gives at the top of page 113 deals with ammonia and hydrogen chloride gas. If they mix, they form ammonium and water. Just ammonium. Ammonium chloride, excuse me. So we've got this NH3 added to HCl, and it produces NH4Cl. Okay, so ammonia, hydrogen chloride, ammonium chloride. Okay, well, understand this. It took nitrogen and hydrogen bonding together through either an endothermic or exothermic process to make this in the first place, correct? So look across the page. How much enthalpy was gained or lost in the formation of ammonia? Because nitrogen and hydrogen are naturally the same. It took energy to get them to bond. What is, look through the chart, it's alphabetized. So find the ends. For NH3, what is the enthalpy of formation? Find it in the chart. It's alphabetized, so find the ends. It's in the final column.
5.9.
All right, it takes negative 45.9, which means this is exothermic, right? When nitrogen and hydrogen bonds to make this exist, it gives off negative 45.9 kilojoules of enthalpy, of heat. All right, what about HCl? What about when hydrogen and chlorine bond to form hydrogen chloride gas? How much enthalpy is gained or lost in the formation of HCl? All right, so then, now let's also look at the product here, ammonium chloride. Find ammonium chloride on here. How much enthalpy is gained or lost when ammonium chloride is formed? right, now here's the problem. Do those numbers add up? Not even close, okay? There is a missing element. So what I'm going to do is I'm just going to say plus X. There is some missing element here that's unaccounted for. Here's the idea. Nitrogen and hydrogen got together to make this. That's how much energy was released. Hydrogen and chlorine got together to make this. That's how much energy was released. But you realize when they react, the nitrogen, the hydrogen, the chlorine, they all get together, and now they're releasing this much to form this. There's missing energy unaccounted for. So mathematically, let's solve. Let's combine these two numbers, the negative 45.9 and the 92.3, and that gives us what?
46.
Careful, they're both negative. I can keep the sign. Not negative plus positive, negative plus negative, so it should be like negative 130-ish. Calculator helps, though you're like, I can do without a calculator. You might actually be right. What'd you get without your calculator, Olivia? I'm sorry? It looked like you were adding them, weren't you? Well, type them in real quick then. This is negative 138.2. Now, if I want to move it to the other side of what is essentially the equal sign, I would need to make it a positive, correct? So let's bring it over as a positive 138.2. Add those together. What is X? What is the missing enthalpy that's unaccounted for here? Negative 176.2 kilojoules. That must be then, class, for these two to react with each other, this must be the enthalpy change that accompanies that reaction. Negative or positive? Which means that this reaction must be exothermic, because it's losing enthalpy. Does that make sense? You look at the individual enthalpies of formation for all of them, and you realize there's something that's going to be here on the reactant side to make the reaction happen. Either it's absorbing energy in, or in this case, it's giving more energy off. In this case, it's giving more energy off. That means this is an exothermic reaction. Yes, sir?
So, in this case, is that just like referring to heat, or is it?
Well, again, assuming the pressure is constant, there's not some weird pressure change, yes, this will all be kilojoules of heat that are released. So in other words, yes, if you were to form solid ammonium chloride through gaseous ammonia and hydrogen chloride mixing, you add heat, you put some heat into it, but the net result is it's going to produce that many more kilojoules of heat giving off than kilojoules of heat used to make the reaction happen. That's the net change in enthalpy that we would track. Yes, ma'am?
You said add negative 314 and negative.
Well, again, when this changes side, this is like the equal sign, right? The yields is an arrow in a chemical equation, but it functions like an equal sign. So remember, whenever you move something to the other side, like if I have x plus 5 equals 7, I put a negative 5 on both sides. Or you could say I move it as a negative 5. That's basically what we're doing. So when it moves over, this is negative, but when you move it over, it becomes a positive over there. Just like any other equation you've solved since you were in junior high. It changes signs when it moves to the other side. Well, let's look at another one of these. Let's suppose, and I think this is another example in the book, we have some ungodly thing like this, and we're mixing it with some oxygen. And I believe this is something in like jet fuel or something, and we're reacting it with oxygen, meaning we're burning the jet fuel, okay? Stuff burns, it burns oxygen. So reacting jet fuel with oxygen, it produces carbon dioxide, and probably, realistically, steam, but water. All right? Notice it's already balanced. That's important. Well, let's take a look at what we've got here. But notice we've got coefficients in this as well. That tells us how many moles. Well, remember, these enthalpies of formation, this is how many kilojoules per mole we have. So we've got to account for the coefficients in the equation. But the math is still pretty straightforward. The first one is we got to look for this guy. The C2H5OH, and where in the world is he? C2H5. Oh, it's 4 times toward the bottom of the first column. What is the enthalpy of formation for that chemical, that compound?
Negative 277.6.
All right. Now, oxygen is an element. And I just realized my camera's not actually showing everything. There we go. All right. Oxygen's an element. Do elements have any enthalpy of formation? No, because it takes no energy whatsoever to form them. They naturally exist. That's why they're elements. So there's 0 there. Plus there's something. So let's put our plus x. You're doing this with me. Not just staring. That's no help. Doing this with me. Plus some unknown energy or enthalpy change. We just don't know what it is yet. Now we come to the carbon dioxide. That's not an element. We breathe it out naturally, but it's still not an element. What is carbon dioxide's enthalpy of formation?
Negative
CO2?
negative 393.5.
But we have 3 moles of CO2 for every mole over here. We're going to have to multiply that by 3. Plus, we have 3 water here, and it is liquid water, yes. So finding liquid water, H2O, what is water's enthalpy of formation? I actually mentioned it a few minutes ago. What is water's enthalpy of formation? H2O, liquid.
Negative 285.8.
All right. So those are our numbers. We just let our calculator do the math. I'm going to start over here on this side. 3 times negative 393.5 plus 3 times negative 285.8. And that's a lot of negative kilojoules. All right. What is that number? When you type it in, let the calculator do all the work. When you type it in, what do we get? For generation of just cell phones, we're slow typing numbers into calculators. All right, you good with that number? Yes, sir, question.
I'm sorry, what did you do for the oxygen?
Remember, oxygen's an element. Elements naturally exist. It takes no energy to make an element because elements already exist naturally. Everything else is formed through some 2 element, like carbon and oxygen came together, and in coming together and bonding, they give off 393.5 kilojoules of enthalpy. Oxygen's just there. That's why oxygen is 0. We don't have anything for elements. Yes, ma'am.
So you're saying if it was just carbon?
If it was just carbon, that would be 0. Yep. And that's why if you look at your chart, like there's no elements on here. All of these are compounds, either ionic compounds or molecular compounds. Everything on here is a compound. All right, now coming over here, I mean, the math couldn't be easier. Negative 277.6 plus 0 plus x. Plus the x, which is our unknown amount of enthalpy that we're finding. How do I move, Abigail, the negative 277.6 to the other side of the arrow? Positive 277.6. And so your calculator already has the negative 2037.9 plus 277.6. And so what is the change in enthalpy when these 2 things react in rocket fuel?
Negative 1,760.3.
Now, is that a big number? Yes, it's rocket fuel. Of course, it's going to give off a ton of energy, not literal ton, but like a ton of energy. A whole lot of heat, okay? Crazy amounts of heat because it's rocket fuel burning to lift a rocket into space. All right, questions on that? All right, that's the first example at the bottom of page 113. Let's take a look at an example that isn't in your book for just a minute, because I want to, like, this one's obviously exothermic, like majorly exothermic. There are endothermic ones as well. For instance, calcium carbonate. It's in like eggshells, limestone, that kind of stuff. If it's heated, it can decompose into calcium oxide and carbon dioxide. Calcium oxide is like lime, any sort of lime substance, not like lime's the fruit. And then carbon dioxide obviously is gas. All right, so let's look up our numbers here. Calcium carbonate, let's find it on our table. And what is calcium carbonate's enthalpy of formation? All right, and then of course there's going to be some additional enthalpy, some change needed to produce CO2, calcium oxide. Oh, it's right, just a couple levels down.
634.9.
Negative 634.9, and then carbon dioxide, we actually saw it just a minute ago, first column.
Negative 393.5.
All right, let's combine on this side to get our numbers. It's going to be around a little over negative 1,000, I think.
634.9.
Negative 1,028.4.
All right, and And then on this side, obviously, we have our x. What do I do with this number to get it over there, class?
Positive.
Make it a positive. So a positive 1207.6. You've already got the negative 1028.4. Just add the 1207.6. And what is the change in enthalpy for this reaction?
179.6.
Kilojoules. Now notice, this came out positive. That means that to make this reaction happen, the reactants had to absorb. That makes this what kind of reaction, class? Endothermic. Endothermic. More energy is absorbed to produce the reaction than is given off. Okay? Massively exothermic, really big negative. In this case, pretty endothermic, positive. Do we see the difference? And that tells us again, we can make sure, okay, yes, there's 3 oxygen. Here's 2 and 1 makes 3. There's 1 calcium, 1 carbon, 1 carbon. It's balanced, but now we're not only balancing the equations, but also saying, how do we actually predict whether energy is given off or energy is released? If so, how much energy given off? How much energy absorbed? Make sense? So we're able to break it down a little bit. I just realized I barely fit that on the screen. Sorry, Grace. All right, let's take a look at another one here. And for sake of time, let's jump to page 115. Page 115. Now let's look at the application number 6. Application number 6. This gives us the full process here. Olivia, read number 6 for us nice and loud there on page 115.
Sodium metal reacts violently with water to produce aqueous sodium hydroxide and hydrogen gas. Calculate the enthalpy change for this reaction.
All right, so we're starting with sodium metal. Class, sodium is Na. If it's metal, that makes it solid. It reacts with water. Class, that's H2O, of course, that's going to be a liquid. And it says it produces sodium hydroxide. What would that be? OH, right? Hydroxide is OH, and it's aqueous sodium hydroxide, plus it produces hydrogen gas. What's hydrogen gas? H2. Now, before we do anything else, we got to balance it. I've got Na on this side, Na on this side. I got 2 hydrogens here. I got, how many hydrogens over here, class? 3. I got 1 oxygen, I got 1 oxygen. It's just the hydrogen that's messed up. Thoughts on what we might try to do? Put a 2 where?
In front of hydrogen.
Over here?
No.
Over here. 3 in front of sodium hydroxide? That would give me 5 total hydrogens, right? That's going to be an odd number.
3.
What if we tried 2 in front of sodium hydroxide? That gets me up to how many total hydrogens? 4. How can I make 4 hydrogens over here? All right, but that would give me 2 oxygen. So I have 2 oxygen?
Yeah.
But now I also have 2 sodium. Can I make 2 sodium? Okay, so in other words, if I put 2's in all the numbers except the hydrogen over here, now everything's balanced, okay? And again, if you had more time, you would have figured it out on your own. But do we see how we first would balance our equation? We've been doing that for over a month now. Now comes the fun part. Sodium, that's an element, isn't it? Does it have any enthalpy of formation, class? No, 0. Does water, liquid water, have enthalpy of formation? Yes, that's not natural. I mean, it's naturally occurring on Earth, but it's not. It's a compound. There's still enthalpy involved in the formation. So, what is water's number again?
Negative
285?
285.5. Wait.
All right, I was about to say, we've seen that number a few times now, but there's 2 of that. All right? Now, what about, now here's where we've got to be careful. Sodium hydroxide comes in a couple different forms. I think it comes in a gaseous form and an aqueous form. And you need the aqueous form. No, it comes in a solid and aqueous form. What's the aqueous form's enthalpy of formation?
Negative 470.36.
But again, there's 2 there. What about hydrogen gas? 0. Very good. It's an element. We have no enthalpy of formation there. Plus X. There's some unknown amount of enthalpy here. All right, so let's multiply these numbers together. 2 times negative 285.8. To get
571.6.
plus the unknown enthalpy we're finding, and then 2 times negative 470.36.
-940.72.
All right, now to solve for x, we got to add the and that gives me what change in enthalpy when these things react. When sodium and water react, and kilojoules will be our unit there. So, when sodium and water react, is it endothermic or exothermic, class? Exothermic. Now that's a pretty good number, by the way. I mean, we're up over 100 kilojoules, like a few hundred kilojoules. That's a pretty good exothermic reaction. There's gonna be a lot of heat produced, a lot of energy given off by this reaction. Questions on how to predict whether a reaction will be endothermic or exothermic, and calculating enthalpy of reaction. Do you see how to use enthalpies of formation to find enthalpy of reaction? Yes, ma'am.
Do you have to memorize these?
No, you'll use the table. Oh, heaven forbid. No, we do not have to memorize these numbers. You'll either be given the numbers or you'll be given a photocopy of the table. It just depends on how many of them. If there's only one or two, I probably just type them out for you. If there's a bunch, I'll give you a photocopy, whichever's lazier for me. Yep, good question. Good. Other questions on this? All right, questions at all of what we covered the last few days? All right, homework for this evening. Homework for this evening is to read pages 109 to 115. Read pages 109 to 115. Reading over all the stuff we talked about the last couple days. On page 115, answer questions 1 through 3, bless you. On page 115, answer questions 1 through 3. And above the homework section is a little practice box. In the green practice box, do number 1, A through C. You're going to practice 3 problems like what we were doing here. Again, so page 115, at the top of the page is a green practice box. Do number 1, A through C. Don't forget, STEM research plans, due tomorrow. I need 2 copies. 1 for me to grade, 1 for the judges. So print it twice or run a photocopy. I also need the grade form on page 199. Page 99 is the grade form. Either tear that out or at least bring your STEM book so you can tear it out when you get here tomorrow. So STEM, give me 2 copies. Again, make a photocopy, print a second copy, whatever. 1 for the judges, 1 for me to grade because I don't want to mess up the judges' copy. But the main homework, read 109 to 115, 115, 1 through 3, and the practice, number 1, A through C. Grace, we hope you get feeling better soon. We miss you, and we'll see you back Monday.